Thanks for the introduction and thanks for coming. So as the title suggests, I will speak about some connection between parameterized complexity and classic time and space complexity. So for the time case, actually the materials are mostly quite old, from 2006 and 2007. The new thing is this connection actually carries over to space case or to space complexity. But in the case of space, it's quite easy to show, in fact. But I try to convince you perhaps there might be in the space version of exponential time hypothesis, and this could be useful to derive perhaps some space optimality of some space algorithms. Okay, so let's go back to the exponential complexity and parameterized complexity. So we have seen a lot of results in this week showing there's a close connection between two areas. But if you go back to see the original motivation of these two areas, you see some difference. So in the exponential complexity, or algorithms, we want to find exponential time algorithm or exact algorithm for NP-hard problems that can beat or that can be significantly faster than the brute force search. But we know that perhaps for some problems there might be not so much hope. So the most famous conjecture is this exponential time hypothesis. So there is no algorithm solving set in time 2 to the little o of n. So using this, we have seen lots of tight lower bounds. And in the case of parameterized complexity, the goal is to isolate some parameters in the problem instance and design algorithms so that the exponential behavior is confined in those parameters. So these are quite different from finding the best exponential time algorithms. And here the working hypothesis is for problem like k-click, there's no FPT algorithm. There's no algorithm solving k-click in time f of k, a polynomial of the size of the graph, no matter how bad this function f is. So you see there are two different things. But in the beginning, quite early, so people realized there's a connection between these two areas. So this result, proved by Donner and a fellow, shows that exponential time hypothesis in fact implies W1 is different from FPT, or equivalently, there's no FPT algorithm solving click. Okay, so this is the connection, and there was some effort to prove the converse, and in fact it was a major open problem. But perhaps now people realize this is extremely hard to prove. One strong evidence is this result by Chen and his co-authors. So ETH in fact implies a stronger statement that k-click cannot be decided in time f of k n to the little o of k. So instead of n, a polynomial of n. So if you can prove that ETH is equivalent to FPT is not equal to W1, then you prove that in case you have an algorithm solving k-click, f of k n to the little o of k, in fact, you can remove this little o of k. That seems to be, at least for me, extremely difficult. Okay? So there's only one direction for now. But in fact, there is an equivalence between two statements, one from exponential complexity, the other from parameterized complexity. In fact, W1 is equal to FPT if and only if k-click, the same problem, can be solved in time 2 to the little o of k log n, a polynomial of n. Okay. So that's, in fact, an equivalence instead of 2 to the little o of k. So if you want to understand this statement, you just need to look at this brute force algorithm solving k-click, which takes time n to the k plus some constant. So n to the k is the time you need to enumerate all k subset of the graph. Okay. Slightly rewrite this term, you get 2 to the k log n, a polynomial of n. So this statement is to say that you can, in fact, improve this brute force algorithm. And the k log n, in fact, is a length of a binary encoding of a k element subset. So we have an equivalent statement between parameterized complexity and exponential time complexity. So another important equivalence is due to Tsai and Judas. They show that ETH fails, or 3-set has a sub-exponential time algorithm, if and only if the miniaturization of 3-set, this is a parameterized problem I will introduce in a few minutes, this problem is fixed parameter tractable. But you will see this is a rather artificial problem. But again, I want to say that there is in fact an equivalence between exponential complexity and parameterized complexity. So one natural question, if you are interested in space complexity, is anything similar in case of space? So if you look at the space complexity, one central problem is, of course, this ST connectivity. So we are given a direct graph G, a source node S and sink node T. You want to find whether there is a path connecting going from S to T. So this is the standard NL complete problem. So in space complexity, and due to a famous algorithm by Savage, we know how to solve it in space big O of log n squared. So it has been a major open problem whether we can improve this Savage algorithm, deciding ST connectivity instead of space big O of log n squared. We want to find an algorithm running in space little o of log n squared. I guess this is an open problem for more than 40 years, or prove this is impossible. So what I want to convince you, perhaps this is a space analog of the exponential time hypothesis. So what is the parameterized version of this ST-com? So of course, we need to introduce a small parameter. So we have an additional parameter k besides graph G and source S and sink T. So we want to find a path from S to T of length at most k. So this is what I call k-ST-com. So in parameterized complexity, it has been asked whether we can decide this problem in space f of k plus log n, or big O of log n. Remember the problem itself, if you view this as a classic problem, it's complete for NL. So this statement, in fact, asks whether in case of k being extremely small, can we solve it in deterministic log space? Okay, if you look at the brute force algorithm deciding k-ST-com, it runs in space k log n plus a linear factor of log n. So k log n is the space you need to store a path of length k. So the next natural question is whether you can improve this to obtain an algorithm with space little o k log n plus O log n. And if so, it's very easy to show that k-ST-com in fact is in parameterized log space. But if you go back to Savage's algorithm, you see that the algorithm in fact solved this problem in space log k times log n. But it looks like an improvement to k log n because you have log k instead of k. But it's clear that log k log n times log n is not really O k log n. If you fix k and let n tends to infinity, you see this goes to log n, this is a little o log n. That's different. So Savage's algorithm is not really an improvement as we want in this question. But given Savage's algorithm, the next thing is you ask whether k-ST-com can be solved in little o log k log n plus a linear factor of log n. So this would be an improvement of Savage's algorithm. Okay. Now we come to the space analogy of this ETH, or this equivalence between parameterized time complexity and the exponential time complexity. So first thing we can show is if you can put k-ST-com as a parameterized problem in parameterized log space, solving it in space f of k plus O log n, then in fact you can improve Savage's theorem. You put ST-com in space little of log n squared. So this would be similar to the case of time. You have k log n in d time f of k poly n imply 3 set in sub-exponential time. And if you go a little bit further, you can prove, in fact, you can weaken this assumption. We only need k-ST-com in space f of k plus little o log k log n. This assumption would already imply an algorithm improving Savage's algorithm. Okay. Again, this is similar in the case of time. If you have k click in f of k n to little of k, then already 3 set in sub-exponential time. So what about the equivalence? Remember, we have some equivalence in the time case. Here we have this equivalence among three statements. So the first thing is KSTCOM in parameterized log space. The second statement is KSTCOM in space little o k log n plus O log n. This would be an improvement of this brute force algorithm. Remember, we have a brute force algorithm storing a path of length k log n, which needs space k log n. Okay, so this is the second statement. The third statement is an improvement of Savage's algorithm. You put KSTCOM in this space little o log k log n plus O log n. So in fact, all these three statements are equivalent. So this is an analogy of this k click in f of k and ok, if and only if this should be O1, so that's a typo. K click in time 2 to the little o k log n poly factor of n. Okay, so these are the equivalents. And the equivalence, in fact, can be showed just by one slide. So I want to show you the equivalence between KSTCOM in paralog space and KSTCOM in this space little o k log n plus a linear factor of log n. So the direction from right to left is the simple observation. Little o k log n can be bounded by f of k plus log n by choosing an appropriate function f. So this is straightforward. The other direction, in fact, you just plug in this Savage theorem with this assumed algorithm solving KSTCOM in space f of k plus O log n. So in that case, I know if I choose k small enough, so for instance, I can choose a path of length d. D is an inverse of f on log n. If you plug in this value to k, you see that I can find a path of length at most d in logarithmic space. What?
I understand the first implication. Maybe I don't understand what you mean by little here.
So imagine you fix k. Then if k is log n is sufficiently large, this is dominated by log n. For each k, you see it's dominated by log n. So you only need to consider for k, fixed k, a sufficiently large number to dominate this fact what's in here.
So little o is in M.
Sorry?
Little o means?
Little o is just a function. Imagine this is the h of something x. So when x goes to infinity, it goes to so it divided by x, it goes to 0. Then you plug in this function h with k log n. That's it. And so now I go back to the second direction. So remember, we can decide and find a path of length at most d, d being this value in logarithmic space. Then we modify Savage's algorithm. Remember, in Savage's algorithm, we do this double squaring things. So now we divide in each recursive step the path of length at most ki into d subpath of length at most ki plus 1 being ki over d. So d is this value. And it's easy to see the total space I need can be bounded in the end little o of k log n. So this is a straightforward modification of Savage's algorithm. So there is a simple proof showing this equivalence between sub-linear space and parameterized space. But in the remaining part of the talk, I want to unify all these things, these three things. The first thing is fpt equals w1 if and only if k click is decidable in time 2 to the little o k log n poly n. The second thing is ETH fails if and only if the miniaturization of k click is fixed parameter tractable. The last thing is the equivalence I showed you in the previous slide in the case of space or KSTCOM. So I want to show you there is a unified framework to show this equivalence, these three equivalents. So this is what we call the miniaturization isomorphism, the isomorphism between parameterized complexity and the classical complexity. So to understand this, we need a little bit more notions. So we're all familiar with parameterized complexity. So here we are given a problem, and besides the problem instance, we need to identify a parameter of this instance. Now, for the exponential complexity, we need this, what we call, is called size measure. So formally, parameterization and size measure are the same thing. They are just two functions mapping a problem instance to a small number, to a number, or not necessarily small. So for our purpose, we need both of them to be computable in logarithmic space. So remember, the parameter is supposed to be much smaller than the problem instance. So kappa of x is the parameter of x, which is small, far smaller than the length of x. And in the case of the size measure, it always represents the length of NP weightiness of x. So let me show you some examples. So for k-click, the standard parameterization is just the size of the k-click. So k I want to find. And you can take the size measure as k times log n. N is the number of vertices in the input graph. So this would be the length of a description of a k-click or a k-element subset. In the case of k-st-com, the parameter is the k again. The size measure, you can again take k log n. So this would be a binary string describing a path of length k. For 3-set, there's no natural small parameters. So for our purpose, we only need the size measure. So we can take the number of variables as the size measure of a 3CNF formula, or the number of clauses as the size measure of this formula, 3CNF. So in the case of tractability, so remember in parameterized complexity, the tractability is fixed parameter tractability. We are looking for algorithm with running time. F of the parameter, a polynomial of the input length. The intractability, so mostly we are only interested in problem in XP. So those problems decidable in time, x to the f of the parameter. So for classic case, in the time case, we have this sub-exponential time. We are looking for algorithm with running time 2 to the size measure of the input times a polynomial of the input length. And for EXP, this would be 2 to the O of the size measure times polynomial of the input length. So for the case of EXP, so exponential time, this would be the running time of or enumerating all NP weightiness of the input x. So this is the meaning of exponential time. For sub-exponential time, of course, we want to avoid such an enumeration. We want to do sub-exponential algorithms. So as we are looking for complexity theory, we also need a kind of reduction. So I won't be giving you the definition of the reductions, but just put the name on the slide. So in case of parameterized complexity, we have FPT reduction and the FPT Turing reduction. And in case of classic exponential complexity, we have this so-called self-reduction, sub-exponential reduction, family reduction, or self-Turing reduction. So what is important for us is FPT and XP are closed under those FPT Turing reductions, and sub-XP and XP are closed under self-reductions. So the well-known specification lemma, in fact, is a self-reduction from 3-set with size measure, the number of variables, to 3-set, the same problem with size measure, the number of clauses. So this is the self-reduction, the specification lemma stated as a self-reduction. Now we come to the space complexity. So in parameterized complexity, we have paralog space. So a problem Q kappa is in paralog space means that I have an algorithm with running time f of the parameter plus O log x. And for intractability, we always look at problems with running space f of the parameter times log x. So one is the addition, the other is the multiplication of these two terms. So in the case of classic complexity, we have sublinear space. Those problems can be decided in space little o of the size measure plus log x. We have also linear space as the intractable problem with running space o of the size measure plus o of log x. And the linear space is clearly those consists of those problems that can be solved by storing all NP weightiness of x. Because you remember mu of x, or the size measure of x, is the length of NP weightiness. So you go through all the possible NP weightiness. So this need linear space. And sublinear space is, of course, you try to avoid storing those NP weightinesses. So here again we have reductions preserving those tractabilities. So I go through this slide. In case of parameterized complexity, we have what we call PL reduction, or parameterized log space reduction. In classic complexity, we have this sublinear reduction family. So as our notion of reductions. So I guess I don't have much time. So now I introduce this miniaturization mapping between these two theories. This would be the mapping sending problem from classic complexity to parameterized complexity. So imagine you have a problem Q together with a size measure nu. So you define the following parameterized problem, as we call it, mini of the Q nu. So the input would be an instance, problem instance X. So you need an additional input, a natural number in unary, assuming this number m is greater or equal to the length of X. The parameter would be the roundup of this nu of X over log m. And the question is the same. You want to decide whether X is a yes instance. So if you see this problem for the first time, it looks completely artificial. But again, it's hard to explain. But what is important is the following. It really works. So we have this isomorphism in the time case. So remember, in parameterized complexity, we look at those problems in XP, and we want to know which of them are really fixed parameter tractable. And in the case of exponential complexity, we want to see which problem can be solved in sub-exponential time. So the isomorphism first carries every problem in sub-exponential time to a problem in FPT. Actually, this goes both ways. So if you have a problem Q nu, so this problem is in sub-EXP if and only if its miniaturization is fixed parameter tractable. And the second is if you have a problem in EXP, it really goes through this miniaturization to a problem in XP. And what is more important, at least for me, is this isomorphism preserving reductions. So if you have two problems, Q1 nu1 and Q2 nu2, you know there is a reduction from Q2 nu2 to Q1 nu2. Then there is a reduction from the miniaturization of the second problem to the miniaturization of the first problem, and the other direction also holds. So this gives you the isomorphism which preserves reductions. I hope you can see from this picture. We can use this miniaturization isomorphism mapping everything faithfully to the parameterized complexity. So everything in exponential complexity to parameterized complexity. But if you speak about isomorphism, of course, you have to guarantee the other direction. So you would ask whether every problem XP would be a pre-image of a problem in EXP by this miniaturization mapping. Of course, this cannot be true because miniaturized problem has a very special form. There are lots of problems in XP have no such form. But we can actually show that if you have a problem in XP, a parameterized problem in slice-wise polynomial time, you can really find a pre-image of the problem in the following sense. You can find a problem in exponential time, which under this miniaturization, you get a mini Q of this problem, which is FPT equivalent to the original problem P kappa. So stated formally, so you start from P kappa from XP, then you can construct the problem Q nu in exponential complex in EXP such that P kappa is FPT equivalent to the miniaturization of Q nu. So this shows that although this isomorphism is not in a strict sense an isomorphism, but if you understand problem as problems that close under reductions, it really gives you an isomorphism between these two theories. Okay? So everything in EXP is mapped to XP, and everything in XP can be traced back to EXP. If you look at this proof, as you can imagine, because it's a very general statement, the problem we construct here is highly artificial, but it turns out, which also involves some combinatorial argument, if you look at this concrete problem, K click, so take this K as the parameter is FPT equivalent to the miniaturization of k-click, taking k log n as the size measure. So this statement shows that if you take k-click, you understand k-click as the classic problem with size measure k log n. Using this miniaturization, it gives you precisely the parameterized k-click problem. And as a simple consequence, as the consequence of previous isomorphism, we can conclude immediately k-click is FPT if and only if k-click is in sub-exponential time. Okay? That's the equivalence. Now we go to the space complexity. Here we have this linear space and sublinear space, and we have parameterized log space and slice-wise log space. Again, this isomorphism just translate everything from linear space to slice-wise space and everything in sublinear space to parameterize the space. So this is the statement, and also this isomorphism preserve reductions. So this gives you the isomorphism carry everything exactly in linear space to slice-wise linear space in parameterized space complexity. Again, we have this surjectivity. So if you start with a problem in XL, you can find a pre-image via this miniaturization mapping. Okay? So again, we can show. So this is the thing we prove quite easily, but now can be stated as a general, can be understood as a special case of this general phenomenon. KST-com, taking K as the parameter, is PR equivalent to the miniaturization of KST-com, taking K log n as the size measure. Okay. The consequence is this equivalence. Okay. So that tells you miniaturization is not only an isomorphism between time complexity, it's also an isomorphism between space complexity. So to conclude my talk, I want to show you an application. So far, we don't really have many applications. So this is one of them. So we know there are lots of tight bound under ETH. So what about this ST-com not in this space, little o log n squared? So here is an application from database or logic. So in this question, we are given a database A. Imagine this is a graph. And we are given a Boolean conjective query phi with d variables. This is a simple first-order sentence using only d variables, but you can reuse them. You are only allowed to use existential quantifiers. And the parameter is phi. We want to decide whether A is a model of phi, or this graph satisfies this formula, or this database satisfies this Boolean conjective query. So we can show this problem can be solved in this space. O log phi log A. It's not very easy, but also not very difficult. And assume ST-com is not in this space little o log n squared, then there is no algorithm improving this. So there is no algorithm using space f of phi, no matter how bad f is, plus little o log phi times log A, the size of the database. Okay, so this tells you using this ST-com Savage algorithm cannot be improved. We can really derive the optimality of certain algorithms. Okay, so that concludes my talk. Thank you.
Are there any questions? Thanks again.